Thanks for having me here. I've never been to Budapest, and the weather seems to ruin my plans for sightseeing tomorrow. Is that everybody hearing well here? Okay?
Yeah.
Well, I'm not the best speaker to be honest, seriously. So, well, Pavlo, I'm from Germany. I'm working for a consulting company as their lead data technologist. It's called Code-Centric, and we are, well, specializing in, or at least I'm specializing in finding leading-edge technologies, establishing them with customers, going there and then just risking my own ass, to be honest, in order to prove that something is actually working and setting it up, optimizing the infrastructure, implementing code for them, doing the proof of concept, whatever. So my early background is, I started back in 2005 trying to find a solution to parallelize an interest calculator written in C or C++, whatever we use for that. So it couldn't utilize several cores in the machine, so I've been looking for means, for tools, how to do this. So I stumbled upon Erlang pretty late, and it was like, it did click, and from then on I played with it a little, and then I just decided to write a book. I've actually written a book. It took me 2.5 years to write an Erlang book, with German Erlang book. Do we have German speakers here in this room?
And fishing.
Only one guy is speaking German in this room. Because the deal is the following. Typically I just ask one question by the end of the presentation, and the first person to answer the question will get the book. So you can consider this. It's actually probably not that funny that Fred's book, because he's awesome. But, well, I do my best describing things like, well, how it's capable of working. And I will go into some details here as well. And also describe urging here, because it is some contribution to this project. So anyway.
Now you just make the subtitle, learn some German.
Yeah, well, actually the problem with this book is officially it's German, but it's 80% Erlang, so. Well, and shell and C, so it doesn't really matter. Java as well, as far as I know. So you should just consider when nobody doesn't want to have it because of the poor German, whatever, I will just give it to Dave. Okay, so, well, what is this talk about? In my job, I look for ways how to introduce customers, well, developers, basically, and architects, wherever the difference is, to concepts of Erlang, and to explain them how the VM works and what are the advantages, what are differences between this one and the world of Java and whatever. So I was always seeking for new ways to describe this. And so, I mean, the very basic thing about Erlang is, in Erlang we have an actor model, which is awesome. We have an actor model where it actually can crash actors, and you can bring them back, or they will be brought back. So this is the point here in this presentation, to describe this. And what is the best way to describe something which has actors and coordinator and something like that? It's, of course, with the movie, right? So let's pick this sequence here. So how not just Java during watching the video. It's a short sequence, or a couple of minute sequence from the second matrix. So the deal here is that Neo, which is the anti-hero, well, when you think of the machine, or the program called Agent Smith, and this is how we can consider this. Agent Smith has one big feature, it's called Neo, and this program has to fight Neo, well, any ghost. So Agent Smith keeps reproducing himself. Neo crashes, kills some Agent Smith clones. They keep coming back and coming back and coming back even more and more and more and more. And this is something that really fits well into the concept of Erlang, into the concept of how VM works, to the concept of actually how the OTP abstracts the work on the Erlang VM. So the video and I will just go on talking. As well, I mean, the problem is that it would make sense if I would stand around for 5 minutes without saying anything. I don't have that much to say, to be honest. I only want to explain this stuff that I have prepared. So, yes, so Erlang. Do we have, we sure have Erlang experts, real experts here. Do we have people like who are absolute beginners or just wishing to find out what it is and stuff? We have, yeah. It's not bad because this conference or this event is actually for people to learn about Erlang. When you want to do real hardcore Erlang stuff, you go to the user conference or Erlang factory in San Francisco. There you will find real hacker who are speaking about things where you need the preparation of several years in order to understand what they're talking about. Anyway, so what is the actor model in terms of Erlang? Think of, well, we call them processes. So think of small units of work which are able to run in parallel, that are not sharing any state. Well, you can make them share a state, but they basically are not sharing any state. They can interact only by passing asynchronous messages to each other. So every actor, every process has a mailbox in front. And this mailbox is just a queue where they stack up the messages, and you need to work your way through these messages, or you can do it selectively, however you like it. But anyway, this is the way how it works. So the very interesting thing about the Erlang VM or the Erlang ecosystem at all is that this actor model is being given for free. So the best way to implement an Erlang program is to cut the whole application into very small pieces that are all parallelizable. Well, you will need barriers where you need to make central decisions then work again and stuff. But anyway, all these small units must be small enough or should be small enough so they cannot influence the stability of the whole thing, because the second part of the awesomeness of the Erlang VM is that you can crash any process, and well, actually you can, you want to crash every process which has a problem with some data or whatever, because the concept is called let it crash. And the idea is when you have a massive parallel system or a system which is big enough, you can predict every possible error situation in your system. So what you do instead, you will have like contracts behind your API calls and stuff like that, where you just will ensure that very hard things will be caught. But all the rest can crash. It will crash processes, and you can implement it in a way where OTP helps you, where you will get these processes coming back again automatically. Of course, there is still a possibility to have the process crashing because of the state, and this is the third part of it. It's the state externalization. Since Erlang itself is a, well, let's call it in functional programming languages, it's not a purely functional programming languages, it's called Haskell. But still, it's functional enough for this that you don't really have objects. So when you want to, well, encapsulate something, it will have to be typically a parameter to your function code. Then you cannot even modify this one because there is single silent in Erlang. So you will create a new state and you will just throw it off as the result of your function. And what you get with things like OTP, with these abstractions, is that this state can be externalized, can be attached to the next call of the function, like message handler or something. So you will get the previous state. When your process crashes, the state, the externalized state, will be reapplied and you didn't lose anything. Still, there is still a possibility that actually the state is the reason why the process crashes. So when you reapply the same state, the process will crash again and again and again. That's why you can even define the OTP. This is the second part, and I will explain. You can define automatic strategy, how you will bring them up, how often they are allowed to crash, and how often they will be brought up before the whole thing will crash in itself. So you watch the movie. Let's just run the same sequence in Erlang. I need to warn you in advance. I have kind of borderline jobs here, but does everybody see it? Probably I should step aside. So we have Agent Smith firing up a couple of blocks of himself, starting the whole thing. Of course, Agent Smith is implemented in Java. So, well, it's not absolutely in sync with the movie, because I mean it's like millisecond exact and stuff like that. I didn't want to do it. It's just showing this concept. So, what you see here, for those who don't know this concept, this is a bit. This is a processor. You can in one Erlang VM, in one kernel process or operating system process, you can have up to 2 to the 27 of processes, like the small units of work that can run in parallel. Well, theoretically, as soon as they don't consume memory, you're fine. When they start consuming memory, well, it's like 350 million or something. It's much. It's a lot. So this is a bit. And what you see here is that Neo, well, how I've implemented this is that Neo is surrounded by a bunch of Agent Smith. He doesn't see the whole environment, so at some point he sees several Smiths, he kills them, and still thinks he reduces their number. What actually happens behind the scenes is that they just keep coming back with new bits. It's just new processes. Completely automatically, and there is no real logic how you implement this in Erlang VM. You will get it for free if you want. This is a configuration stuff. Okay? So, well, the sequence will run and run and run and run. There is a couple of actors here. The whole matrix is, well, it's kind of built of several actors. There is this Agent Jackson that you have seen. It appears for probably 3 seconds or something. And there is this woman, which is half a second there, and so on and so forth. So back to Erlang itself. So what is OTP? Well, OTP is, well, it's the secret sauce when you want to implement a real professional application in Erlang, because it gives you a couple of real basic abstractions that are needed, that are best, that are best utilizing the concepts of what the Erlang VM gives you. The abstractions are, the first abstraction I will briefly talk about is the application. So you can package your application, your Erlang application, in a way where you can utilize things like hot swap, for example, in the way where I think Dawson was speaking about this non-zero zero downtime systems and stuff like that. So when you have an ATM switch standing around somewhere, you don't want to send a tag guide there in order to upgrade things. So you can just package an application in a way where you can just send binaries there, it will get upgraded. And the concept of the hot swap in the Erlang VM is that you can have up to 2 different versions of the same module, the same piece of code, running at the same time. There are rules when they will be eliminated, and the new version wins. I'm sorry, did you see Jackson already? Yes. It was basic, right? It's just there for a couple of seconds. Okay, anyway, back to Erlang. The application, you do some configuration. I will show you the code of this. We will step through it. So the application is just a bundle of your modules, how you will upgrade stuff and all that. So you can just see it as a big runnable unit in your Erlang VM. So the next very important thing is that these processes are per se in the Erlang VM. They have same rights. So there is, well, not automatically, it's a given that one process is more important than the other process. So what you can do is you can link these processes together. You can link them in a way where both of them know of each other's existence. So when one of them crashes, all the others linked to this process will crash with it together. So you can imagine infrastructures you can build on top of this feature. What you also can do is you can monitor a process. Well, process A monitors a process B. That means that process B doesn't have an idea that it gets monitored by A. So there is no crash relation, or however you would call it, between them. But a very interesting thing, you can trap exits of processes. So you can make one process a little bit higher priority in what it does. So it will get automatically from the VM, it will get messages in its mailbox, thrown into its mailbox, where it says that processes are dying something. So it can actively react on it and do something. So when process A is trapping exits and sees, okay, process B has crashed, it can decide, let's bring it back, because some shit happened there. We have up to, well, around about 500 of them right now. Okay. So, exactly. And what OTP gives you is, it takes one level higher. It gives you abstractions for this. You can have a supervisor and a worker, whatever they are. A supervising process typically doesn't do any work. It doesn't do computation or whatever. Its only job is just to observe when something crashes. It has a declarative configuration where you can say, what is the strategy when things crash? So this supervisor can decide, okay, I will bring them one after the other. I will bring them all together when one of them crashes. I will bring them up again. Or I will crash myself if some thresholds are reached. So in this case, the whole hierarchy will crash. Okay, so we went down. The whole hierarchy. And on the other hand, there is an abstraction of a worker. A worker is, actually something that typically doesn't supervise. People are still trapping exits in workers because sometimes you need to do this. For example, when you deal with non-OTP code in your application there. But still, the worker just does work. It reacts on messages or whatever it does. There are several different worker kinds in the OTP ecosystem. So the supervisor can have children. It will have children. These children are either workers or supervisors themselves. So you can have a whole tree, a whole hierarchy of all these actors interacting with each other in a way where supervisors can make whole decisions. When a sub-tree of this crashes, I will bring it up completely back again. So you can ensure a zero downtime system using this means. You still have a lot to invest a lot of thoughts how you implement a system like that, but the Erlang VM combined with the OTP framework, it gives you a lot of mechanisms how to do it comfortably. So workers are typically, the easiest one is a server. So there is an abstraction of a generic server. The server can get asynchronous and synchronous calls. Well, actually, there are no synchronous calls available natively in the Erlang VM. So they are simulated so it's just a spinning weight there. Exactly. So the server's task is get messages with a state, create a new state, react from the end of the message. That's basically it. Then the next very important worker, it's kind of hybrid. It's a hybrid. It's a finite state machine. It's a generic finite state machine. So what it is, it's actually a state machine where you just can step from one step to the other until you decide to die or just to stop the whole thing. So you typically take this FSM as a coordinate of processes there. And I have FSM here in my case is the matrix, or you can also call it the director of this sequence. It just coordinates It just sends messages at right times. It just coordinates the sequence itself. So before I die speaking about code, let's just look at the code. Oops. So let's start with come on. So this is, well, it's built with rebar, so whenever you do, these days, whenever you do real complex applications, this one is just a small one. It's on GitHub, by the way, you can look it up, the whole source code there. So rebar is much more comfortable than the way you build applications, OTP applications, the way they are being built originally. I spent like 50 pages describing how it works originally, and then I said in 3 lines, just said use rebar. Well, it's really real hard. It's sometimes not predictable what happens there, but you need to deal with it. So anyway, this is the application descriptor, and this application descriptor has some keywords here. What is really important here is the environment setting. And this is the screenplay part. For those of you who are not familiar with the syntax of Erlang, these curly braces are, well, defining tuples. Everything that is starting with a small letter is an atom. And so what you can do in the Erlang VM, there are two different sorts of actors. When you have, as in my case, thousands of Smiths, you don't want to call them like Smith 1, Smith 2, Smith 3. It doesn't matter at all. You just will have a bit. Because atoms are being handled completely differently in the Erlang VM. I probably should explain this. What Erlang VM gives you is garbage collection and heap and garbage collection per process. So you can actually have up to 2 to the 27 of heaps in the Erlang VM. So every single process has its own heap. They are not interchanging, they are not exchanging anything except messages. So garbage collection is basically done per heap, per process. There is a couple of exceptions to this. First of all, the atom memory is completely outside of this. So atoms don't get really garbage collected, they just get reused. It's a symbol, it's just a symbol. It's not even a variable or a string, it's a symbol. It's something that defines things. And there is also a memory, a sort of shared memory for bigger binaries, which is starting with 64 bytes. And binaries are pretty cool in Erlang because you have native mechanism how to pattern match binaries. Is everybody here familiar with the term pattern matching? It's not like regex, it's a little different. Well, this is a real cool thing because what happened to me after I started doing Erlang is in every single language I'm looking for pattern matching and I'm desperate, missing it. And, Python, why not? Why not? Really? It should be simple. So I've started studying Haskell, not hoping even that it will ever hit the mainstream, but it's pretty cool. So anyway, exactly. So you can even pattern match binaries, bit streams, because there is a difference. Binaries are 8-bit bound. So anyway, bigger binaries are get references. So you have a reference count, and processes are just keeping references to binaries, and VDM takes care of. They also keep references to sub-binaries and stuff like that. It's probably a little bit complex here for this talk. But anyway, big binaries will just get referenced. When they don't change, you don't need to move around big portions of data between processes from one mailbox to the other, so it's just a reference going there. And sometimes there are situations where processes don't release references and you have memory leaks. Well, you need to take care of things like that. Of course, it's not like running through the world with a pink glass or with the pink glasses. You need to be realistic. Okay, back to code. So the screenplay is actually just a sequence of tuples describing one step. So I'm using time coordination here because I mean they are all running in parallel to each other, exchanging messages and killing each other and stuff like that. So I need a coordinator. And the whole screenplay goes down and down and down until the last one with the Smith looking stupid comes here. It takes like 20 seconds to do. Where is it used? This is the Gen FSM thing. It's called Matrix FSM. And, well, you typically in the Gen FSM, in the thin state machine module, you will have different steps, like different, I mean, it's a token going from A to B to C and so on and so forth. So you have different states here, like start, click, whatever. So in my case, it's just step. Every single step is called step. And I take just one tuple from the screenplay, reducing the screenplay list one after the other until it's empty, and that's it, then it's gone. And it keeps sending messages to the actor that you find in the first element of the tuple, the step tuple. And this is actually the coordination. The rest is happening in the, in the actors themselves. That's not a good idea. Sorry. Okay. So the next thing is, let's look at the main supervisor here. Well, the main supervisor's job here is it's on top of the hierarchy, and it defines several children it will have. And these are all the actors. So it defines a couple of own children like workers, and it defines the supervisors, like in case of Smith supervisor, who is responsible for its own children, its own clones. And this is basically how you define the whole, the whole mini world, the tiny world, however you call it here. Smith supervisor is pretty boring. Nothing happens there, except it just provides a comfortable API function to clone things and to find the current agents. And it has only one child, it's a worker, it's called Smith Clone Server. And it does almost anything. It just comes up, it keeps dying, keeps coming back, and this is the Erlang VM or the OTP just gives you that. You don't take care of this. Again, for those of you who didn't touch it yet, most of you did, but still, the process dies, the process comes back. The process gets its state reapplied. You can go on from there. Let's look at the Neo server. Well, Neo server has different roles here, has different tasks here. It has to think, it gets asynchronous messages all the time, and it does something with that, like beating Smiths, killing them, thinking of Trinity of things, and the whole coordination, you can easily look it up on the GitHub. It's much easier than to talk about it, just to read the code. It's a couple of, things I have to implement here, like deciding based on which weapon Neo is using and how many Smiths are around, finding the ratio of those to kill and stuff. So it's just like, it has nothing to do with learning, actually. And beating is just a time coordinate thing. Okay, so what do we learn from all that? First of all, Erlang is awesome. Yeah. Who have node folks around? I'm just kidding, I'm using Node myself. Anyway, Erlang is awesome for systems where you can or you want to have a massive parallelism, which is a very interesting thing how it's implemented in the Erlang VM. It's pretty complex. You have a scheduler, or basically one scheduler in a normal setup, one scheduler would be running on one core. Because Erlang itself, the VM, it kind of simulates an operating system. It wouldn't really, well it does, but it wouldn't really rely on kernel and stuff like that. So it simulates a small operating system. That's why it's called processes, right? Okay. So it's this simulation leads to pretty nice things. So we have a scheduler which is responsible for a run queue, where everything that has to happen will be just brought from this queue, and this queue will be just emptied one after the other. So I will pick up the process, will give it work, then we get the next one, the next one. I/O is basically asynchronous. In this case, even also with utilization of equal and kqueue depending on the operating system. So compared to Node, for example, it also has an internal event loop, of course, when it's about asynchronous I/O. So the next thing is that a process gets a number of reductions. So it's bytecode and time-relevant thing. Bytecode instructions and time-relevant thing. So it will be off-scheduled when the reductions are at 0. So it will just count down and okay, the next one is on. So this is how it ensures this parallelism internally. Of course, you can bump reductions. You shouldn't do this, but you can. In cases where you just can't predict, or you just don't want it to be off-scheduled by the scheduler, in some cases because of complex computation or even synchronization mechanisms in there. Almost nobody does this, but you find it in every single code base. Pretty interesting. Anyway, so what do we learn is not only that Erlang is awesome, but it gives you a possibility to quickly start when you want to implement a massive parallel system. Think of 2 to the 27 parallel processes being able to run in parallel. It gives you this, it doesn't give you this for free, but it feels like getting this for free when you're a programmer. You still have to take care of a lot of things. You will have to take care of barriers because parallelism leads at some point to synchronization where you need to merge results, whatever. It ensures through its abstractions that the concurrency doesn't hurt that much. Erlang is for time sharing. It's, as I told you, it's a reduction-based scheduling, so it's for time sharing. You wouldn't take Erlang for like heavy applications in the mathematical area, or something you will probably upload this to C, and the problem that you will get there is that when you do this integration between Erlang and C, you will run into the C code, and when this C code takes forever, you will completely block the scheduler that has actually managed the process running into the C code. So, well, people are, at Ericsson, as far as I know, are, well, at least elaborating and investigating how they can teach the C code, even interoperate with the scheduler as well. But from my point of view, it's yet experimental. But maybe there are successes already. So anyway, so the concurrency doesn't hurt that much. Think of things like single assignment. So you cannot override things intentionally or even accidentally. So you always have to create a new state thing from the previous state. You will not override anything, so side effect freeness or freedom. And asynchronous message passing, the only guarantee it gives you that between two processes, when process A sends to process B messages, it will be in the same order between them two. It's the only guarantee. You cannot build on further guarantees because they are not there. But for many situations when you have millions of connections from clients, for example, chat rooms and stuff like that, where they need to interact with each other in a synchronous way, this is the best fit, this is the real perfect fit for that. People implement web applications based on Erlang. I'm pretty skeptical about this because my saying is that you can also use your shoes in order to open bottles of wine. but you probably shouldn't do this. But anyway, people are experimenting with this, and it's, I mean, it's free world, right? And yeah, so this is basically it. Thank you very much for listening. Before I take questions, I need to get rid of this one. So once again, who is everything I've talked about and much more is described in this book. So again, who is speaking German in this room? Okay, the question is, what language was Agent Jackson implemented in?
Basic.
Java.
You're not speaking German, man.
Java.
Wrong. Next one. Agent Jackson wasn't implemented in Java. Who said basic? Okay, you get the book. Congratulations. So let's do some questions. I think we're completely all the time, right? Let's do some questions. Any questions? Yes.
Is there any best practices to transform everyday problems into sample-based models?
If only I knew it. Well, you need to have a specific use case probably in order to benefit from the actor model. It's also not everybody's thing because people are, well, used to think procedurally, well, step after step, and suddenly you realize a lot of parallel things are running around, and how do I do coordination and stuff like that? I'm totally lost, oh my god. Back to the question, you need to have use cases. When you really have, you wouldn't do something like that here. You can do this on Node.js, well, minutes as well. It's not the point. When it's about massive parallelism, when you cannot predict how many actors will run around, how many it is, how they will interact with each other, you will create a model. You first need a model, and this is what OTP gives you when you define children and configuration for children, like this declaration of what children and what supervisors do what there. And whenever you have this model, then you can decide, okay, it needs to be actor-based because I have different roles, I have different priorities, I have different heaviness of them, and I have a lot of messages flying around between them. But to be honest, it's not that easy. It's really not easy. I had to learn this because Erlang was actually my very first touch of actor model, and my first code was like, oh my god. I mean, Erlang is a pretty simple language. It's a language. You start with it like, well, after 2 weeks you can write code, right? The real complexity comes with the VM itself and how you deal with what the VM offers. And this takes years, probably centuries, to properly understand it and properly tweak this. Did it kind of answer the question?
May I add to that?
Yeah.
In terms of what use cases to take and where Erlang fits, one of the things about Erlang is there's this low latency built into the way it does it, because it has the power of the space as well as reduction based, meaning you can't have one guy that steals up all computing time. In Node.js, you can be more or less screwed by one process just taking up very long time. In Erlang, if you have a guy that takes up a long time when you're processing a request from him, he'll be run out by the scheduler because he gets a number of reductions, which means you get low latency. All the small stuff gets to run. So if you have situations where that's important, it's not good for high throughput yet. That's some of the research we're working on to help participating in that will help on that. But low latency.
I can bump up my reductions as hell and steal the computation time
You can.
from everybody.
Out of the box.
I'm just kidding.
Yeah. But you could do that also. You could do
You can do this, but it's kind of semi-deprecated.
Not on a multi-core machine.
Excuse me?
Not only if you're running on a multi-core.
No, you can. Then it's right. Yeah, you're kind of caught in one schedule. Right?
I thought that was the problem with Node, that it doesn't handle multi-core.
No, well, Node is fixed to one core, right?
Yeah,
so one single thread.
Basically,
Yeah.
sorry.
This is actually comparable with how you would have a well, an Erlang application with a lot of NIF calls. And those live calls will decide how well your time sharing will work. And this is comparable to this. Node has its own use cases actually, because what it does well is it completely eliminates concurrency from you. But you cannot scale this in a way you can scale this on the Erlang VM. So this is, the comparison doesn't work, doesn't really work. Yeah.
I think a great example for Erlang use cases is you can see here there's a supervisor tree, and under that there's a bunch of processes. And if you imagine a web server running this, like Node.js registry, there's thousands of calls coming in every second. And let's say one person has misconfigured their client, and it's always sending invalid HTTP requests. What actually happens inside the Erlang VM is the supervisor at the top is happily running all the concurrent clients that are behaving, and there's one of them that just keeps dying. It sends an invalid request, and that process that's handling that individual call dies, and another one comes up to top its place. And the result of that is you spend less time worrying about edge cases in production, things you didn't think of. Every time a new browser version comes out, it comes out with new quirks and new problems. And the rest of your customers and your code is running fine, and you can sit there and say, show me the things that are crashing more often. And you can look at that, and you can look at it in real time, and you can decide what to do about it. And in most other languages, boom, that's it, it's all over, everything's down. You forgot this edge case, and your entire business application is down. And in Erlang, what's happening is that supervisor tree is crashing and crashing and crashing. It gets restarted higher up.
Well, the term real time is a kind of
Soft real time.
yeah. It's kind of wrong these days because they use it for big data as well. Well, anyway, notice is, for example, well, it's good for when you even don't need processes or connections or whatever, when you just push events through. This is also for that. Whenever you have to deal with these connections and want to keep them, want to have this state externalized and stuff like that, you would probably go with Erlang VM. But the decision is very difficult. I mean, most of the time it's kind of, well, belly driven, like I like or I don't like. So anyway, for those of you who don't do Erlang but want to try it, I would suggest quickly learn the language and then start off with OTP from the beginning. Because without OTP you will probably, well, I don't know. For most of the programmers, this is the best set of abstractions to work with. You can even write applications without OTP abstractions, it's still processes passing messages and stuff like that, but you have much more best practices to follow there and to keep in mind. And the OTP just gives you framework. And whenever you're far enough with this programming, you will break out of OTP pretty quickly, I promise you. You will find a way because it doesn't offer what you need. Then you can decide if you want to do to provide a long behavior. It's all code behaviors there, by the way, application and server and whatever. You can even implement own behaviors and extend the system in a way. But at some point you will just decide, hey, come on, just let's do it the classic way. Lean early, clean early. Okay, more questions?
More questions from the lunch break.
Okay, let's do it in the lunch break. Thank you very much again.